It's my pleasure to speak to such a distinguished group of nuclear colleagues in the United States and elsewhere. This morning, in the short time I have, I will introduce a little bit about Westinghouse, talk about the AP1000 design, and particularly its safety features and how it mitigates accidents, particularly station blackout. Talk a little bit about the licensing process progress we have around the world, and also some construction progress that we have around the world, and then briefly conclude with some socioeconomic impacts of building reactors, particularly in India. Thank you. Westinghouse is 125 years old this year. We're very proud of that. Founded by George Westinghouse. We've had some unique technological firsts, DC technology. And I must say, my colleague from General Electric, we competed with Thomas Edison for AC versus DC, and even 125 years later, they're still competing with our friends from General Electric. So, in commercial nuclear power, the first pressurized water reactor outside of Pittsburgh and Shippingport in the 1950s. So, significant first for Westinghouse. Today, we're a different company. We are a 100% nuclear company. We no longer build appliances. We no longer do a lot of things that Westinghouse used to do. So we focus 100% of our activities in nuclear, whether it's new nuclear plants such as AP1000, nuclear services, nuclear fuel, and nuclear automation. Worldwide company, about 15,000 employees spread throughout the world. As I was introduced, I'm located in our Asia headquarters in Tokyo. And Asia being the area of fastest growth. Just a few comments on AP1000 technology. AP1000 has been in the development for about 25 years. We started in the mid-1980s developing the AP600, predecessor to AP1000. About 600 megawatt plant. AP1000 actually is around 1,100 megawatt plant. But I credit the engineers and scientists with the foresight 25 years ago to look at passive technology. And it's to their credit that I think we are where we are today with the AP1000. Considerable investment, 25 years, and we often say that we've invested hundreds of millions of dollars to prove that gravity works, and it still works. Mr. Isaac Newton was correct, gravity does work, and we proved that, but it's taken hundreds of millions of dollars to prove that. As we look at the evolution of nuclear power, there's several different ways to achieve increased levels of safety. When we talk about jet-free plants, we typically talk about increased levels of safety. And if you look at this tree, there's two branches of the tree. One way to achieve those levels of safety is by adding active systems, more redundant systems, additional trains, additional pumps and valves. And we can achieve those levels of safety and levels of redundancy by adding those active systems. The other way that we chose on the right-hand branch is the passive way. AP1000, General Electric, PSBWR, we heard about the advanced pressurized heavy water reactor and its passive features. So that's the other branch of how we achieve those levels of safety. And we believe that passive is the right way because it's simpler, has fewer safety grade pieces of equipment, and less stress on the operator. And the ultimate heat sink is ambient air, the atmosphere. So if we look at the AP1000, some of the key features, safety features, top of the list is no reliance on AC power. And if we look at the events at Fukushima, unfortunate events at Fukushima in March of this year, not having to rely on AC power is a significant benefit for reactor design and safety systems. No safety-related pumps, so there's no pumps that need to activate in the event of a loss of power, station blackout. 72 hours without operator action, so there's much in an emergency event. There's much less stress on the operators. Now, I must add that there are active systems in the AP1000 design. Those are non-safety-related active systems, and the operator has the ability to activate those active systems to mitigate the event. The passive systems only come to play if those active systems, non-safety related active systems, are not available, such as in the instance of the station blackout. But the first line of defense is always to utilize the systems that are available to the operator. If those fail, the passive systems kick in. In-vessel for severe accidents, we utilize in-vessel retention. I'm not going to talk about that today, but our system is to use in-vessel retention to prevent the escape of a core from the reactor vessel. One of the benefits of passive technology is design simplification. And the system on the left would be a typical, what we call Generation 2 reactor, such as the Westinghouse reactors that are around the world today. Many active systems, many penetrations into the containment with piping, valves, and pumps. And if you compare that to the system on the right, the passive AP1000 technology, all of the safety systems are contained within the containment building. So there's no safety systems, safety-related systems that are outside of the containment building. So considerable simplification, both in design, operation, and ultimately in construction. So if we look at what passive safety features can drive, particularly if we look at the lower right-hand side, those compare the various quantities of material of a typical Generation 2 reactor to a passive system. So significantly fewer pumps, safety-related pumps, significantly fewer safety-related valves, significantly less cable, significantly less concrete, particularly significantly less seismic building volume. The seismic building volume is a significant driver to construction time and construction cost. As I mentioned before, if we look at the last bullet, the operating margins, we have significantly increased operating margins and accidents are mitigated through the use of active systems that are available, and the passive systems only come into play if and when those active systems are not available. Again, you know, we have a saying that size does matter. Again, if we look on the picture on the left, we compare a traditional Generation 2 reactor. This happens to be Sizewell, which is a Westinghouse 4-loop plant in the United Kingdom. So if we look at the footprint, if we look at the safety-related systems in color, and we compare that to the footprint of an AP1000 on the right, you can see the significant difference. And when we have visitors come to our construction sites in China, they're amazed by the size. And when I say amazed by the size, the smallness of the AP1000, the smallness of the footprint compared to a traditional, typical 4-loop or even 3-loop reactor. So if we look at some statistics, like an AP1000 compared to a Sizewell plant, is about a fifth of the concrete and about a fifth or a sixth of the reinforcement bar. So again, less concrete, less rebar means less cost, and also, even more significantly than less cost, means more schedule predictability and shorter schedule time. And in nuclear, with very large capital costs, construction time is paramount, and the ability to control and assure construction time is paramount to keep the costs within reason. I mentioned before testing. Since the mid-80s, the AP600 and the AP1000, the AP600 being the predecessor, has been extensively tested. And these are just some of the pictures of the testing that we've done in the United States and around the world to prove the various passive systems work. And again, as I mentioned before, we proved that the gravity indeed does work through extensive testing. A very current event, station blackout. Of course, what happened at Fukushima was a station blackout event. And the AP1000, even starting 25 years ago, took that into consideration. So in the event of a station blackout, the reactor is maintained in a safe shutdown condition for 72 hours with absolutely no operator action, no on-site, no off-site AC power, no AC power is required whatsoever in the first 72 hours to maintain the reactor in a safe shutdown condition. And after from 72 hours to 7 days, we would use other sources of water on site, and after 7 days, additional sources of power and water would be implemented to maintain long-term safe conditions and cooling. Again, looking at station blackout, which is very relevant to today's safety environment, 3 things you need to do to prevent a station blackout. One is core cooling. You need to cool the core. You need inventory to cool the core, and you need to control reactivity. The chart below just shows the decay heat, and it's particularly important to maintain that cooling in the early stages of the event because the decay heat is high and obviously tails off as time goes on. The other thing is containment cooling. You have to get the heat out of containment to the ultimate heat sink, which in the case of the AP1000 is the atmosphere. And then lastly, spent fuel cooling. As we saw in Fukushima, you can't ignore the spent fuel pool. You must maintain cooling of the spent fuel pool at all times. So if we look at the scenario of the station blackout, 0 to 72 hours, you have a reactor trip because of station blackout. And I have some animations coming up that will demonstrate some of these features, but you need to remove the decay heat, and we do that passively through the passive core cooling system. And you have to remove the heat from the containment, so we do that through a passive containment core cooling system. 3 to 7 days, we have ancillary diesel generators, non-safety diesel generators on site that we would activate to provide additional sources of water, such to fill the water tank at the top of the AP1000 containment. I'll explain that a little bit in a few minutes. And then beyond 7 days, we would have additional sources of water that we can bring into the site to provide long-term cooling for the containment. Because if the containment cooling system continues without the addition of water, the other water is needed to actually cool the containment for the ultimate heat sink. So I'm going to, hopefully these will work. This is actually a demonstration of a LOCA. It's similar for a station blackout. You have a break in the primary system. The pressurizer responds to that break by trying to make up water as the system is losing it.